All right, guys, so let's discuss again the mathematical models of control system. We're going to start discussing the mathematical models in this chapter. And then this discussion will keep on going next week. And then whatever we are learning, of course, we're going to be applying pretty much throughout the semester on different control systems. So the process that we are learning in this chapter is very important. So make sure if you have any question at any time, make sure to stop me and ask. So in time domain, all the control systems are written down with a differential equation. And that's why most of the time we are not really solving those control systems in time domain. Although, again, we need to understand how to write down the characteristic equation of the systems in time domain. But solving differential equations, especially if they are higher order differential equations, is very complicated. So it's easy for us to go from time domain to the frequency domain using Laplace transform. And when we do that, your equations from integral differential equations, they become basically simple algebraic equations in frequency domain. And then they are pretty easy to solve in frequency domain. It's a straightforward process. If you learn that process, it's very easy to solve. And of course, we're going to be using MATLAB as well along the way to help with the problem solving process. And then once we have the solution in the frequency domain, we can again find a lot of characteristics without even coming back to the time domain. Your stability characteristics, how to design the system, a lot of stuff can still be done in the frequency domain. But if you want to see, of course, the time domain expression and you want to plot it, then you can go back to the time domain from the frequency domain using the inverse Laplace table. And then you can see the time domain expression. Again, writing those expressions and solving those things in time domain itself sometimes becomes pretty complicated. We are going to be looking at what we call transfer functions. Transfer functions we have used in circuit analysis as well. Anybody remember what does transfer function mean of a system? Ratio of output versus input. That's the transfer function. And generally, transfer functions are very commonly used in control systems and signal processing, even in circuit analysis when you are studying the characteristic of filters. So we're going to be looking at the transfer function, and then we'll be solving for those transfer functions in the frequency domain. And we can also solve, if we know the transfer function, we can also find the output of a system based on its input. So again, as I said, we're going to be using Laplace transform. And we will be using partial fracture decomposition, because when you have an equation written in the frequency domain in Laplace transform, then to convert that back into the time domain, you have to write that equation. It's usually given in the fractional form. So that fractional form has to be written in the partial fraction form in order to apply the inverse Laplace transform using the table to bring it back to the time domain. So we'll be doing all those things. How many of you remember partial fraction decomposition? How to do that? Okay, some of you do, some of you don't. Okay. Now, you guys need to know that. That doesn't mean you have to show me all the time how to do the partial fraction decomposition, but it's important to know those things. We're going to be using MATLAB, and you took DSP, some of you took DSP. We use MATLAB and DSP for the partial fraction decomposition. So that's what we're going to be doing as well. In control system, we're going to be using MATLAB and the residue function in MATLAB for the partial fraction decomposition. But again, you need to know how to do the partial fraction decomposition. If I do ask you a simple fraction and show me how to do that, then you should be able to do that. But for practical purposes, it's not practical to keep doing partial fraction decomposition once you know it. You don't really have to keep doing that. And that's when we're going to use basically the residue function in MATLAB to perform that. And you will see how easy it's going to become your problem solving process. But again, that does not mean you should know that you have no understanding of partial fraction decomposition. You need to know how to do that, of course. We're going to be looking at both block diagrams and signal flow graphs, and these are two common ways to to represent control systems. And we're going to be doing that next week, not today, but next week in this chapter. Both of them are in this chapter. Differential equation of physical systems. There are two types of variables for pretty much all systems. One is called through variable, and one is called across variable. So for example, electrical system, we already know current is a through variable. It passes through components. And voltage is an across variable. You measure voltage across a component. So the example of through variable and across variable for electrical system is current and let's say the voltage. And likewise, you have mechanical system and electromagnetic systems and all those systems. Each system has through variable and across variable. And this is a table from the book that shows you different through variables, integration of those through variables, across variable, and integration of those across variable. So electrical systems, of course, current is the through variable as we discussed. And when you do the integration of current, you get charge because current is basically rate of change of charge. So when you integrate current with respect to time, you get basically charge. And voltage, of course, is the across variable. And when you do integration of the voltage, you basically get the flux. We discussed that in power systems as well. Your induced voltage is rate of change of flux according to Faraday's law of electromagnetic induction. E induced is dphi over dt or n dphi over dt, basically proportional to. So when you're finding the flux, this is the integral of the induced voltage. And that's what we discussed in power system, I think, this week. Some of you are in power system when we discussed that in power system under the Faraday's law of electromagnetic induction. Mechanical variables, as you can see, force, mechanical translational variable, and rotational variable. Your force is the through variable, and then you integrate the force, you're gonna get the momentum as your integrated of the through variable. Velocity is the cross variable, and displacement difference is integration of the velocity, because velocity or speed is rate of change of distance. And likewise, mechanical rotational, the variables are given to you. Our concentration mostly is on the electrical side, of course, since we study electrical engineering mostly. So mechanical is part of control systems, but again, my expertise are not mechanical system and your expertise are not mechanical system. So we're going to be concentrating a lot on the system itself, and then we're going to be looking at the electrical aspects of those, most of the systems, basically. And again, this is a summary, very small, hard to see. That's something that you do not do when you're presenting, that you don't put anything that is hard to see. So that's an example, not to put a slide, something like that. I should have put it on two sides, basically cut it. Actually, I can cut it because I have inductive storage, capacitive, and energy dissipation. I should cut it and increase the size. I'm going to do that actually. But make sure that anytime you're presenting, whatever you're presenting should be easy to see to the audience. So this is a bad example of a slide that you should present in a presentation. But anyways. So again, you can see the inductive elements, electrical inductance for electrical spring, translational spring, rotational spring, all of those, they are inductive storage. That is, they store energy in some sort of what you call the magnetic, well, electrical inductance, of course, it's magnetic. A spring is not really magnetic where it stores energy. But basically, they are showing you that the voltage or the across variable is the differential of your through variable for the inductive storage element. That's what they're trying to show you in this table. Capacitive storage, your through variable is the derivative of the across variable. That's the capacitive storage example. And then you have the energy dissipation, electrical resistance. Basically, linearly related current is linearly related to the voltage. Damper is linearly related to the distance and all those things. So you have the first one is the example of through variables, across variable as a differential of the through variable. The second example is through variable as a differential of the across variable. And the third one is the variables are proportionally related to each other, either inversely proportional or directly proportional. Yeah, I'm going to fix this thing later on. Differential equation of physical systems, and again showing you different quantities presented in this table 2.1. You have the through variable, force, torque, current, and all those things. So we already saw these things over here. No need to go over this slide. Differential equation of physical system. How to represent the differential equation of physical systems. And this is something that we did that in circuit analysis, of course, when we were discussing the parallel and series RLC circuit. So this is a parallel RLC circuits, as you can see. And this equation represent the voltage across each component, which is the same. How did we write this equation? We apply KCL on this circuit and we wrote this equation. So this is your current IR, this is your current IC, and this is your current IL, and this current is equal to the current source, which is RT. Total current coming out of the current source is equal to the sum of all these currents. And then we applied Ohm's law to write IR. We apply C dV over dt, which is a relationship between IC and the voltage. And then we applied the integral of voltage across your inductor as the current passing through the inductor. And then again in circuit analysis, we solved this thing. Right? We're not really solving this thing right now. But in circuit analysis, we solved this thing. We had 3 cases. Anybody remember those 3 cases? So we had underdamped, overdamped, and critically damped cases based upon the 2 frequencies that we discussed. I left this thing. I wanted to ask you. So since you have the current source in the circuit, the voltage response is going to be comprised of 2 components. One will be the transient part, one will be the steady state part, right? So in this case, what will be the voltage, steady state voltage? Anybody can tell me? What will be the final value of the voltage? It will be 0. Why? It is 0 for sure. Why? But that doesn't make it 0 though. It's 0 because of the inductor. Yes, because of the inductor. Because the inductor, when it is fully charged, and this is a DC source, is going to act as a short circuit, right? If it's going to act as a short circuit, so the output voltage eventually is going to become 0. So the final value of the voltage, that steady state voltage value, is going to be 0 because inductor is going to be fully charged and short. And the transient source free response is going to be dependent upon what type of damping do you have. If it's an overdamped circuit, then of course transient response is simply exponential decay. Overdamped circuit, anybody remember what will be the characteristic equation of the overdamped circuit? S2T. So both depends upon the exponential. S1 and S2, of course, they're the roots of the quadratic equation, the characteristic equation, and both values are negative. So it's going to be negatively decaying response. Now, another important thing in control system that we also discuss in circuit analysis, or we discuss in circuit analysis, is what is the dominant root? That is, which part of the equation is going to define the shape of the curve? Anybody remember that? Which part of, so this equation is comprised of 2 parts, A1 S1 and A2 S2. Which of this part is going to define the shape of the curve? That is how fast it is going to go down. Well, S1 and S2, so Napier frequency is alpha, and for the parallel RLC circuit, alpha was what, 1/2 RC, if I remember correctly, right? And then you have omega naught, which is the resonant frequency, which was 1/square root of LC, and then you have omega d, which is the natural resonant frequency for the underdamped circuit. That is, if you have the response underdamped, then what is the frequency of this sinusoid? That is omega d, and that is given by omega naught square minus alpha square, when omega naught is greater than alpha. Then of course your case is underdamped. Now when you have the overdamped, then your omega naught is smaller than alpha, so your two roots, and the two roots of course we calculate as S12 negative alpha plus minus square root of alpha square minus omega naught square. So of course for the overdamped circuit, the two roots are going to be negative alpha and whatever the value of this plus, and then negative alpha minus this. So both values will be negative. So my question was, so alpha is Napier frequency, which is this, of course. There are not two alphas, there is only one alpha, but there are two roots using this equation, S1 and S2. My question was, we're gonna again, it's part of the control system studies, so we should discuss it at this time since it is coming from the circuit analysis. That which part, let's say you have A1, give you an example. Let's say this is comprised of 4e negative 3t plus 7e negative 20t. Let's say, the two roots, S1 is negative 3 and S2 is negative 20. So the question is, which part of this equation is going to define the plot of the system? Which one? 20? Okay. 3. So we have two answers, 3 or 20. Which one is the correct? One of them is going to define it. It's going to be 3. It's going to be 3. And why it is going to be 3? Because that's the frequency, remember, right? 3 is the radian per second, or time, of course. So when you have the complex plane, S plane, Laplace plane, then this is the Laplace plane. This is S is equal to negative 3, and this is S is equal to negative 20. Now, when you're writing e to the power negative 3t, you can also write this down as e to the power negative t over 1 by 3. It's the same thing, right? That means it is going to take 1/3 of a second, or 0.33 seconds, to drop down to e to the power negative 1, which is the time constant, right? Which is basically, what was that, 36% of the peak value. Whereas if you have negative 20t, which can be written as negative t over 1/20, it is going to take 1/20 is what, 0.05, right? Or 0.05. It is going to take 0.05 second to drop down to 36%. So it is dying very quickly. It is dying much quicker than this one. It's the first one is dropping down to 36.6% of the peak value in 1/3 of a second. The second one is dropping down to 36.6 of the peak value in 0.05 seconds. So much faster than the first one. So the longer it's going to last, that's going to define the shape of the curve. And that will be the dominant root of the system. So many times, the system equation can be very large. But you will, when you start observing the system, you say, well, this part of the system is going to die quickly, this part of the system die quickly. So I'm only left with just this part of the system. And that's the whole thing, basically, that I need to understand the characteristics of the system. So it's very important to understand which part of the system is useful and which part of the system is relatively useless. Yes? We can call it time constant. But in this case, it's not really time constant of the system since we have two values. But we want to see that, again, time constant definition was RC circuit and RL circuit, that when the transient response drops down to 36% of the peak value. That's a time constant, right? For RL or RLC circuit. This is RLC circuit. So we have two values, but in a sense, it's the same thing because we are saying, okay, how fast it is dying down, because you have two curves. Basically, if you plot that thing, then it is comprised of two curves. This is one curve, and then this is the other curve. And then you're adding these two together to plot that thing, right? So the question is, which curve is going to really define the shape? And the answer is, well, this is going to die down very quickly. That means this curve is the dominant curve that is going to be defining the shape of the response. So that's the concept of the dominant root. So whenever you see two values of S1 and S2 in an overdamped system, or critically damped, whatever, overdamped has two values, of course, then make sure identify what is the dominant root. And that dominant root is going to define the shape of the system's response. And the dominant root is going to be whichever is closer to 0. Whichever value of S is closer to 0. If the value is far from 0, you don't need that basically, because that's not really defining, that's dying down very quickly. But the one that is close to 0, that's sustaining for a long time. So this discussion is going to come pretty soon in the future as well. So I just wanted to continue the discussion at this time. All right, what is the underdamped response shape? E minus alpha t A1 A1 cosine omega dt plus A2 sine omega dt. That's what we studied in circuit analysis. And this is basically an underdamped response. This response can also be given by E minus alpha t B cosine omega dt plus theta. Instead of having both cosine and sine, we can give B cosine omega dt plus theta. B is usually A1 square plus A2 square, and theta is tangent inverse of A2 over A1. And in the book, in the table, you will see equation similar to that instead of this equation in the Laplace table. And this response, of course, as you can see, this is the underdamped response. And what is the critically damped response shape? Yeah, A1 plus A2t. It's a linearly decaying exponential response. So these are three responses that we discussed in circuit analysis as well. And again, we're going to be seeing this type of responses in control systems. Linear approximation of physical systems. Mostly all physical systems are non-linear actually. They're not linear. All practical systems are non-linear. But within the constraint, you can assume them to be linear. There are two requirements for linearity. The system has to follow the superposition principle. That is, if you have one input given to the system that is producing an output, and if you have another input that is producing another output, if your input is a combination of these two inputs, then the output should be the combination of the two outputs. That is superposition principle, and that follows linearity. Homogeneity basically requires that if you are scaling up and down any variable, multiplying a variable by an amplifier, then the output should also be multiplied by the same factor. So in general, linear system follow that if x produces y, then ax1 plus bx2 will produce ay1 plus by2. That is, the output will be multiplied by the same factor as the input, and x1 will produce y1, x2 will produce y2, and their combination is going to produce the combination of y1 and y2. If your system is following this, then it's a linear system. And as I said, most of the systems are non-linear, but you can approximate them within constraint to be linear system. Laplace transform. Why do we use it? We use it to make our life easy, to be very honest. So If system can be approximated as a linear system, what we are using, all systems are linear for us. Laplace transform can be used to convert the integral differential equation, the equation that we had for the circuit, or any other equation that is integral differential equation, that can be converted into simple algebraic equation in the S domain. And then we can solve it very easily. And that's why we use Laplace transform. These are the Laplace transform pair. Laplace transform of any function ft can be calculated using this equation. And inverse Laplace transform, that is if you want to go back to the time domain, can be calculated using this equation. S is the Laplace transform variable. Of course, we are not using this. If in the engineering class, we do use it. But in this class, we're just going to be using the table. So this is the table, Laplace table, that we will be using for all of our systems mostly. So there are multiple pairs, Laplace pairs given over here. There are some of them that are important that we'll be using very frequently. For example, we're going to be using the step function very frequently. If a step function is given to you, then, so if input, let's say input is given by RT usually, input is a step function, then the Laplace transform of the input is 1 over S, which is given in here. So that is one of the functions we'll be using very frequently. This we will be using very frequently as well. Laplace transform of the exponential function, e to the power negative alpha t, 1 over S plus alpha. Sine and cosine, we use them not very frequently, but still. T to the power n, t squared, t cube, we do use it. If our equation is written in time domain, if it's differentiation and integration, then we have to use Laplace transform of differentiation and integration, then these pairs are used. And let's see, the other one is that is used very frequently is this one right here. This one is used very frequently. And yeah, that one is used very frequently. And what is this one? This one is also used frequently right here. Those are for the underdamped system. These two on the right side, they are for the underdamped systems. This is when your underdamped system is excited by an impulse function, and this is when your underdamped system is excited by a step function. So if you want to go and look at the response in time domain, this will be the response in time domain for those two. So there are a few of them we will be using very frequently. Some of them we will not really be using much. All right, let's see what do we have. Solve for the voltage across the capacitor for the parallel RLC circuit, as we discussed earlier, using the Laplace transform. So the parallel RLC circuit that we had, let me redraw it again. And of course, we solved this thing using differential equation and circuit analysis. We're going to do the same using Laplace transform and using the table. This is RT, which is given as 5 UT. This is R, which is given as 2 kilo ohm. L is 1 millihenry. And C, 2 microfarad. And again, this is just the practice of Laplace transform. This can be a part of a control system, not entirely the whole control system, but part of the control system as band pass filter basically. Assume that the system was relaxed before t is equal to 0, so there was no energy stored in inductor or capacitor. If the system is relaxed, inductor and capacitor has 0 energy stored. IR, IL, IC. All right, so first we write the equation, what we had earlier, that is RT is equal to IR plus IL plus IC, and we are trying to find the voltage across each component because each component is parallel, so voltage is the same. And our RT is V over R plus 1 over L integral of V dt plus C dV over dt. This is all from circuits. Don't forget, of course, relationship that capacitor current is C dV over dt and inductor voltage is LDI over dt. LDI L over dt. These are our basic relationship between current and voltage in capacitor and inductor. And using those relationship, we wrote that equation down. So now we're gonna go ahead and apply the Laplace transform on this equation using the table. All right, let's assume since we are taking all variables, instead of putting 5 ut, I'm just gonna assume that this is current source. So I'm gonna assume that the current value is I and ut, and later we're gonna put down the value I is equal to 5. So everything is gonna be in terms of variable. So IUT, if you look at the Laplace transform table, again, ut Laplace transform is 1 over s. So we're going to go ahead and write this down as IUT is I over s. S lowercase s, not uppercase. V over r, so 1 over r is of course constant. Laplace is not applied on the constant, only the time function. So Vt is the time function. And let's say Laplace transform of Vt is V as a function of s. This is all Vt, remember, it's a time domain function. Vt, Vt, and Vt. So it's a time dependent voltage. And then 1 over L integral of V dt. So 1 over L is constant. Integral of V, go back and look at the integral. This integral of ft, let's increase. Integral of ft is fs over s plus 1 over s integral from negative infinity to 0 ft dt, right? Now, if you have some value of the function from negative infinity to 0, then this has to be included. But in our case, since our input, our system is relaxed, really there is no value from negative infinity to 0, this is going to be 0 for us. So simply the Laplace transform of the integral is going to be fs over s for us. So 1 over L fs, that is vs over s, plus C dV over dt. So C is a constant, so C is going to be here. Laplace transform of dV over dt. dV over dt. So K is power 1, of course, dV over dt, and that is going to be s to the power 1 f of s minus sk minus 1. Again, all the values before t is equal to 0 are 0. Therefore, these all are going to be 0. The only thing that would be left is s to the power 1 f of s. So S V S. So now we are going to write this equation down in terms of Vs, because that's the one we are trying to find. Vs on one side of the equation, other things on the other side of the equation. So let's take the Vs as a common factor out. Vs 1 over R plus 1 over SL plus SC equals I over S. So Vs is going to be I over S divided by 1 over R plus 1 over SL plus SC. 1 over R plus 1 over SL plus SC. We're gonna reorganize this equation because we want to write the equation in terms of a polynomial in the numerator and a polynomial in the denominator. That's what our goal is. So I over S is the numerator, and in the denominator, SLR is my common denominator. And this will lead me to SL plus R plus S square R L C. So Vs is this S and S cancelled out. And I have I times RL divided by S square RLC plus SL plus R. And we don't really want any coefficient with the highest power of the polynomial. So we're going to divide numerator and denominator by RL and C to get rid of this RL and C with S square. So we're going to have I divided by RL and C. So I divided by C over S square plus S divided by RC plus 1 over S. And now we can go ahead and plug in the numbers to see what is our polynomial. So my capacitor value is 2 microfarad. My I is 5, so 5 over 2 microfarad. 5 over 2 is 2.5. Micro becomes mega in the numerator. So 2.5 exponent 6 in the numerator divided by S square plus S over RC. Let me go ahead and pull. R is 2K and C is 2 microfarad and L is 1 millihenry. I is 5. Okay. Okay, 1 over RC. $250 and 1 over LC. That's 5 exponent 8 or 500 exponent 6 in engineering. 500 exponent 6. So this is my equation, polynomial over polynomial. It's a proper fraction, as you can see. What are proper fractions? Anyone? What are proper fractions? Numerator is power, highest power on numerator is smaller than the highest power in the denominator. Very good. So when you're solving for the partial fraction decomposition, your fraction should be proper fraction. Otherwise, you will have a residue and partial fraction decomposition. But this is a proper fraction, of course. Now, this equation can be seen. Let me go back. If you look at, let's see, if you look at this relationship right here, omega n square, s square plus 2 zeta omega n s plus omega n square. And then we compare it with our equation. Let me write down this equation here so we can compare it easily. We have 2.5 exponent 6 divided by Vs equals s square plus 250s plus 500 exponent 6. So this is an easy way to solve for Vt. And we are looking at this relationship right now. Omega n square over s square plus 2 zeta omega n s plus omega n square. So omega n square and the denominator right there, that omega n square is this thing, omega n square. And then 2 zeta n omega s. So 250 is 2 zeta omega n. Omega n is the natural resonant frequency. Omega d basically is omega n here. And zeta is your damping coefficient, which is between 0 and 1. We're going to discuss that later, basically. So in order for this equation or this fraction to look like that, what do we need? We need in the numerator, of course, 500 exponent 6. That is omega n square. That's what we need. Omega n square is 500. We already have 2.5 exponent 6. So if we do 2.5 exponent 6 divided by 500 exponent 6 times 500 exponent 6, we are not changing anything, divided by s square plus 500 exponent 6, which is omega n square. All right, now we can easily calculate what is the value of omega n, which is the square root of 500 exponent 6. Increase the font size. Okay. So this is my omega. Omega n square is 500 exponent 6. So omega n is square root of 500 exponent 6. 2.23614. That's my omega n, or 22.3, 22.36 kilo. I should keep it in format ENG. Short ENG. So in this case, my omega n is 22.3 kilo radian per second. From this, we can find out the zeta value because 2 zeta omega n is 250. That means 2 times omega n, zeta is 250. So zeta is 250 divided by 2 times omega n. 5.59 exponent negative 5 or 0.00559 or 0.0056. So zeta is 0.0056. Omega n is 22.36 K. And then we have 2.5 exponent 6 divided by 500 exponent 6. So let's say Q is equal to 2.5 exponent 6 divided by 500 exponent 6. So 5 milli. So if I go back to my solution and if I write this down as 5 milli, 5 exponent negative 3 times 500 exponent 6 divided by s square plus 2 times zeta is 0.0056 times omega n, which is 500, which is 22. What was that? 22.36 exponent 3. S plus 500 exponents. So now I have the equation written in the form that is given in the table. This is omega n square. This is zeta. This is omega n. And this is omega n square. Is it correct? 2.5 exponent 6, 5. No, is it? Let me see. Five exponent negative 3 times 500 exponent 6. 2.5 exponent 6. Yeah, that's correct. Okay. All right. Okay, so now if we apply that relationship that we had in the table, we can write down the time domain expression. If we apply, so our equation is in this domain now, and we have omega n over 1 minus zeta square. So let me write it on the board. So my Vt is omega n over 1 minus zeta square. So omega n is 22.36. I'm just going to write this down. Omega n over 1 minus zeta square e to the power negative zeta omega nt, e to the power negative zeta omega nt, and sine of omega n 1 minus sine of omega n square root of 1 minus zeta square times t. That's about it, right? Yeah. And omega, and what is zeta is less than 1, which is it is less than. So this is my solution for my voltage. So if we go back and write this down, Vt is equal to omega n over 1 minus zeta square e to the power negative zeta omega n t sine omega n 1 minus zeta square times. And let's go ahead and calculate the numbers. So my omega n is 22.36, my zeta is 5.5, and these are the two quantities I need. So let's say A is omega n divided by square root of 1 minus zeta squared. 22.36 exponent 3, 1 minus zeta squared is 1 basically, because zeta is 2 is small, so it's the same thing. 22.36. 22.36. And then negative zeta omega n. So let's say B is equal to zeta times omega n, 125, so e to the power negative 125t sine omega n square root of 1 minus. So again, 1 minus zeta square is just going to be pretty much 1, because zeta is 0.05 and we take a square of that, that's even going to be smaller. So this approximately is 22. Actually, we are multiplying it. Yeah, so it's going to be 1 times that. So it's going to be the same, 22.36 approximately. We can confirm that C is equal to omega n times square root of 1 minus zeta squared. 22.36. 22.36t. And this is 22.36 kilo, so that's going to be kilovolt. So I'm going to put UT and then kilovolt. So that's going to be your solution. Yes. Oh yes, we do. Sorry, I forgot that. You're right. So we're going to multiply the whole thing by that. This whole thing is multiplied by that to 5 exponent negative 3. So we go here and then we multiply this whole thing by 5 exponent negative 3. So when we do that, we're going to change kilo will be cancelled out by 5 exponent negative 3, and we're going to multiply 5 times 22.36. This kilo is going to be, so 5 times 22.36. Let's go back. And 5 times 22.36. 111.8. So that's going to be 111.8. And that will be the final result. We are putting UT because the input is starting at time t is equal to 0. UT is the step function, remember. We discussed the step function again in circuit analysis. So UT is the step function. And since the input is starting at UT, we want to show that this voltage is valid when time t is equal to 0 or greater than 0. It's not valid. This solution is not valid for values of time which is less than 0. That's why we are going to put that UT over. Or you can just write down for time t greater or equal to 0. If you don't want to put UT, then you will have to put that this solution is valid for time t greater or equal to 0. So using Laplace transform table, not Laplace transform, but Laplace transform table, we found the solution of the voltage. The important thing over here is that I showed you is how you're going to write this equation such that you can use the equation given in the table. Because our equation is not exactly the same that is given in the table, but we can kind of morph it in the form that it looks like what is given in the table. So this is, if you want to use it, the table. I'm going to show you, if you don't want to use the table, then how you're going to do that. Yes? Exponent, which one? Yeah, you're right. Omega n is exponent 3, right? Yeah, so that is missing. You're right. So let's go ahead and fix this. 22. So I'm going to write down 22360, let's say. 2236, whatever the value was to be exact. Let's see what the value was. Where's my mouse? Right here. Omega is 22360, right? So 22360. Yes. Because when we wrote down this equation, we wanted to write it down in whatever form was there, right? Omega n squared. So we wanted to write this down in this form: omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So that we can use this. So in order to write this down, what I did is right here, I multiply and divide this thing by 500 exponent 6. And that's why I got this 5 exponent negative 3. Because 500 exponent 6 is omega n squared. So I need that in the numerator. So when I multiply these two together, I'm going to get 2.5 exponent 6. Right? So I'm trying to basically create the form to be the same as given in the table so that I can use the time domain function to write the equation. Any question about this? Okay. If you do not know that specific relationship, this one, if you do not know that, then how you're going to solve this thing? Let's look at that as well. So if you don't know that, then you have basically this equation right here. This is the equation that you're using to solve for VT. And if I don't know that relationship, if I don't have the table, I don't know what omega n zeta, how you're going to write that, nothing. I only have this fraction. So how I'm going to take this fraction and get the result? Let's look at that then. 2.5 exponent 6 s squared plus 250 s plus 500 exponent 6. We're going to write this down into partial fraction. Solution for VT using partial fraction decomposition and inverse Laplace transform. So my Vs, which is equal to 2.5 exponent 6 over s square plus 250s plus 500 exponent 6, s square plus 500 exponent 6, can be written as 2.5 exponent 6. And then I'm going to make the factors of the denominator, s square plus 250s plus 500. So what will be the roots of the denominator? In MATLAB, you can easily use roots function. And you can find roots of any polynomial using roots function. So I have 1, you put the coefficient of s squared, 1, coefficient of s, which is 250, and coefficient of the constant, which is 500 exponent 6. So I have two roots, negative 125 plus 22.36 exponent 3, and then positive. So it's a complex conjugate function. We know it's a underdamped function. So I can write this down as S. Now, when you see these roots and when you're when you're writing the factors, when you're creating factors from these roots, remember factor is going to be s minus each root. That's going to be the factor, because when you're calculating the roots, basically, how do you calculate the root? If you have a factor x plus a, you equate it with 0, and the root of this is negative a. So when you see over here, these are the roots. This is the root. So if you're creating factor, you're going to subtract this root from the x value, in this case s value. So s minus the factor, and the factor is negative 125 plus j 22360, and s minus the factor negative 125 minus j 2236. So whatever polynomial, you can always find roots using MATLAB. Of course, this is, if you want, you can apply the quadratic equation, but why when you have the roots function available? So I can write this down in terms of partial fraction as a over s plus 125 minus j 22360, and then if your denominators are complex conjugate, then your numerator will also be complex conjugate. So this will be the complex conjugate of a. All right, anybody remember how to find the value of a using partial fraction decomposition? Of course, once you find a, you know a conjugate is the conjugate of a, so you don't have to find conjugate. You have to find only one basically. But how are you going to find value of a from this equation using partial fraction decomposition? Anybody remember that? Okay, and then you're right. The first part is right. So multiply both sides. Both sides means that you have this side on the right hand side, and then this is the left hand side. This or this basically. That's the left hand side. So multiply both sides by the denominator of a, and then what you're going to do next? I'm sorry? Equal to what? I'm sorry. No. I'm saying that two sides that we are discussing. What Trevor said, multiply both sides. Both sides mean this is one side, and this is the other side, because these two are equal to each other, right? We want to create this to be equal to that, right? But we are putting it in terms of partial fractions. That's the complete fraction. Now we are putting in terms of partial fraction, but it has to be equal to that. So the first step, as Trevor said, that we multiply both sides. If you want to know a, we multiply both sides, that and this, by the denominator. But once we do that, so let's do that first. Multiply both sides by the denominator of a in order to find a. So let me go to the, what is on the next slide? All right, let me insert a slide here. So slide. So I'm going to do this, and I'm going to then show you. Many of you know residue function, then I'm going to show you the residue function as well. So to calculate or to find a, multiply both sides by the denominator of A. That's the first step. So when we multiply both sides by the denominator of A, what we are going to get, this is going to be cancelled out. Well, let's just start from here. 2.5 exponent 6 times s plus 125 minus j 22360. So this factor will be cancelled out on the left side because it's going to be the same thing in the numerator, and only this factor is going to be in the denominator that will be left. S plus 125 plus j 22360. So on the left side we will have, what is the 2.5 exponent 3? 2.5 exponent 3 and this factor s plus 125 plus j 22360. And on the right side I will have a plus a conjugate s plus 125 minus j 22360 divided by s plus 125 plus j 22360. So when I multiply both sides again means this right here, this or this, whatever. This is easy because you can cancel out the factor. You multiply this thing by the denominator, which is 125 minus j 22360. This factor will be cancelled out. And when you multiply this, of course, a is going to be here, and then a conjugate times this factor divided by this factor. So that's the first step. Now, what I was asking next, so now what should we do? Because again, how are we going to find a from this equation? And what is that value? You evaluate at the root, of, you evaluate for the root of the denominator of a. So the root of the denominator of a, you're going to evaluate both sides on that. So the root is negative 125 plus j 22360. And evaluate at the root of the denominator of a. That is, s is equal to negative 125 plus j 22360. You're going to evaluate at this value. So when you evaluate at this value, 2.5 exponent 3 over negative 120, and I'm showing a step by step. I'm not going to show step by step every time we are doing it, but this is the first time I'm doing it, so I'm showing is each step. 260 plus 125 plus 2j is equal to a plus divided by so what do you see here now? Negative 125, positive 125 cancelled. J22360, negative J2360 cancelled, which gives you 0. 0 times a conjugate will be 0. So on this side, only a will be left. This negative 125, positive 125 is cancelled. And we have 2.5 exponent 3 divided by j, 2 times 22360. So from this, we can find A as A is equal to 2.5 exponent 3 divided by 2 times J 2. I'm sorry, exponent 6 or 3? Exponent 6. Okay. Why did I put 3 over here? Exponent 6. Okay. Let's go ahead and fix this. Exponent 6 and exponent 6. Exponent 6. J2 to 3, 6. That is going to be the value of A. So A is 2.5 exponent 6 divided by 2 times omega n, right? Omega n is that? Omega n times I. So this is going to give me negative J 55.90. Negative J 55.90. I want to separate this so that people don't get confused. So this is one part. Let's see if you're getting the same result. So new slide. All right, so what is my partial fraction decomposition now? My Vs, is A, which is negative J 55.9, negative J 55.9 divided by S minus negative 1. Let me go and check one thing real quick in the table. S plus A, so I'm just going to write down in terms of plus instead of minus. So S plus 125 minus J 22360, and the other one is the conjugate of that. So J 55.9 divided by S plus 125 plus J 22360. This is the partial fraction decomposition. Okay. How do you do partial fraction decomposition in MATLAB? Many of you already know about it. People who do not know about it, let's go ahead and show them as well. In MATLAB, we have the residue function to do the partial fraction decomposition. So let's go back to this basically. So if you have to make the partial fraction decomposition of this proper fraction, then in MATLAB, this is how you're going to do that. R and P are the two outputs where R is going to hold the numerator values and P is going to be the roots of the denominator. And then you use the residue function. First, you're going to enter the coefficients of the numerator polynomial. So in this case, you only have the constant value, 2.5 exponent 6. 5 exponent 6. And you don't have to put brackets if you have only single value. You can if you want. And the denominator is s square, the coefficient is 1, 250s, coefficient is 250, and 500 exponent 6. And this is your result. So you have, don't worry about the negative 18, because that's just such a small value, you can just ignore it. Negative 55 exponent negative 18. Let's just ignore this thing altogether. That's pretty much 0. It is showing you 0 actually for the second one. That should show 0 for the first one as well. I don't know why it is showing negative 80. But anyway, so this is your number. Negative J 55.90 correspond to the first root, negative 125 plus J 22.36. And then J 55.90 correspond to the second root. And that's what we got in our calculation. So I'm going to go ahead and I'm going to cut this thing. Cut. And I'm going to put it in the slide. So if somebody want to check it. So observe now, compare these two. Negative J 55.90, negative J 55.9, and the denominator root is negative 125 plus. Now remember, this is the root. This is not the factor. This is the root. Roots. So when you're creating the factor, you're going to do S minus the root. S minus negative 125 plus J 22360. S minus negative 125 minus J 2236. So you don't have to go through the partial fraction decomposition. Again, you need to know the partial fraction decomposition. But if I do ask you that show me the work for partial fraction decomposition, then you got to show me the work. But if I give you, most of the time in exam or something, if I give you like 3 problems or 2 problems that require you to do partial fraction decomposition, generally I ask you for 1 problem, which is generally easy. That show me the work, and then the problem that is require more work for partial fraction, I just ask you, you can use residue function to solve that. So that's what I do generally. So again, make sure you know partial fraction decomposition. But most of the time, we're not doing partial fraction decomposition, except the first time I'm going to show you. I still have to show you, a couple of more problems, but we're going to be using the residue function most of the time. Okay, so now we have the partial fraction decomposition. Now what? So now we're going to go back to our table and see what we can do with this thing. So let's go back to the table. So we have basically, what do we have? We have A, and we have A conjugate. We have S plus A, and we have S plus A conjugate. That's what we have, right? So if you go back to the table, and you will see what is 1 over S plus A, and you will see that right here, 1 over S plus A is e to the power negative 80. So we're going to use that relationship. So let's go back. And we're going to write down first inverse Laplace transform. Inverse Laplace transform, which will give us Vt from Vs, and that is going to be A e to the power negative At plus A conjugate e to the power negative A conjugate. That's what we are getting here, right? A e to the power negative At, A conjugate e to the power negative A conjugate Et. Of course, we know the value of A, and we know the value of lowercase a and uppercase A, both. So let's put down those values. Vt is equal to, what do we have? A is negative J 55.9, right? Negative J 55.9. Negative J 55.9 e to the power, what is that? Negative 1. So A is 125 minus j 22360. So negative 125 minus j 2236 t plus A conjugate, which is j 55.9 e to the power negative 125 plus j 2236. So this is directly from the table, right? Again, if you have any question at any time, please ask. So far we're just using partial fraction decomposition, and then we went back to the table and we saw that which relationship in the table is going to work with that partial fraction that we got. And then that is the relationship that is working. So we wrote that down in terms of that. This is not the final answer, because remember, our final answer is, we already know the answer, which is something like this, what we did here. The answer is something like this. It's an underdamped function, right? E to the power negative 125 is the exponential, and then sine 22360 is the sine. So it's an underdamped function. Our answer so far does not look like this. That doesn't mean we cannot get to that answer. So how are we going to convert this into a trigonometric function? Let me show you the steps. So first, what we're going to do, we are going to VT negative j 55.9. This is complex number written in rectangular form, right? In the polar form, how are we going to write this thing? Yes, 90, exactly. 55.9 angle 90. So let's write this down. 55.9 angle negative 90 degrees. And then I'm going to break this down. E negative 125t, E plus 22360j. And then again, I'm going to write this down in terms of polar form, 55.9 angle 90 degrees. E negative 125 t, E negative j 22360. Okay. Now, this thing, this number in the exponential form can be given by 55.9 e to the power negative j 90 degrees. Now you're going to ask me why. I will ask you why actually, before you ask me why. Okay. So, and again, I used it. The reason I say I'm going to ask you why, because I explained this in DSP and many of you did take DSP. Why we can write that number 55.9 angle 90, which is complex number written in polar form as 55.9 e to the power negative j 90. What we are using here? Euler's identity, exactly right. Very good, excellent. So we are using Euler's identity. Remember Euler's identity? I'm going to just do it here so you remember it. E to the power jx is cosine x plus j sine x, and e to the power negative jx is cosine x minus j sine x. So that's the two relationship of Euler's identity. So now you have e to the power negative j 90, e to the power negative j 90. So if you put it here, which will be cosine 90 minus j sine 90. Cosine 90 is 0 and sine 90 is 1. So you're going to get negative j1. So negative j1 times 55.9 is negative j 55.9. So that's how we wrote this negative. I did not really have to write the polar form, by the way. We can just jump from here to here, irrespective. So that's how we did that, negative j9 e to the power negative j90 s times 55.9 is going to be negative j 55.9, and same thing goes for this. All right, so now we have this, and we have some common factors here. So I'm just gonna do it here. This implies Vt 55.9 is common, so I'm gonna write down outside. And then e to the power negative 125t is common. It's common. And then what do I have? E to the power negative j90, e to the power j 22360t. So I can write this down as e to the power j 22360t minus 90 degrees. And then from this, I can write down e to the power negative j 22360 minus 90 degrees. 22360. E to the power jx plus e to the power negative jx. So if you add e to the power jx and e to the power negative jx, what you're going to get? You're adding these two. You're going to get 2 cosine x, right? E to the power jx is cosine x plus j sine x, e to the power negative jx, cosine x minus. So when you add them together, negative j sine x and positive j sine x will be cancelled out, and you're going to get 2 of cosine x. This will be equal to 2 of cosine x. All right, so what do we have then? 55.9 e to the power negative 125t. Two times cosine of j 2 times cosine of 22360t minus 90 degrees. 22360t minus 90. All right, 55.9 times 2. Let's see, 111.8. And cosine 22360 minus 90 is cosine A minus B is cosine A cosine B plus sine A sine B. So cosine A cosine B, cosine 90 is 0 plus sine A sine B, sine 90 is 1. So when we simplify this, we're going to get sine of 22360. And this is something that we already got using the relationship. But if we do not know the relationship, then this is how you're going to get. So this is purely using partial fraction decomposition and using the table without knowing the relationship. We are just using e to the power at. We are not using the second order relationship. So there's an other, let's go back to this. Where is it? There's an other thing that you can add in the table, actually, that if you have this relationship. So let's go ahead and add this. Let's add this in the table. So one other relationship is if you have Fs A over, how should I write this thing? S plus A plus A conjugate S plus A conjugate. You have this, then your relationship is going to be, let's go back and try to find the relationship between the two. So you have 2 times the magnitude of the numerator. You have 2 times the magnitude of the numerator. And then in this case, A is in this case, A is what? Alpha plus j omega n, right? That's A. Alpha plus j omega n. Because our alpha was 125. Where is it? Yeah, here. Alpha was 125 and omega n was 22360. So alpha and j omega n. Let's see. Let's go back. Let's go back. That's going to be e to the power negative alpha t cosine of omega n t plus that was the phase of numerator plus phase of the numerator. So this is the relationship that we had. Let's compare it what we had. 2 times magnitude of the numerator, which was 55.9, e to the power negative alpha t, alpha was 125, cosine omega n t, and phase of the plus phase of the numerator. Phase of the numerator was negative 90, right over here, negative 9, right? So if we have this relationship, if we are getting this partial fraction decomposition, then instead of going through all that thing that I showed you, again, you should know that, but I'm not asking you to do the whole derivation. You can just apply this relationship and get the result. So let's add this over here. Again, this is the same thing as what we are having here, right? But that applies in any case, as long as your system is under damped system. Question? You will have to do some practice, of course, right? Make sure you do practice. Without practice, it's not going to work. Let's go back to the notes at home when you're relaxed, and then review everything, do the problems yourself. Don't just read the problems, always do the problems. If you read the problems, you're not going to get it. When you do the problems, then you're going to get it. But I'm gonna put that there because we're going to be using that very frequently, that relationship. Most of the time, I don't remember even this. This is very hard to remember, this one. That is pretty easy to remember. This is similar to what we had in DSP as well, one of the relationship. Do you remember, Gabriel? Right? Oh, yes. Yeah. Yeah, sure. 2 slides after. So this one. Okay. Got it? All right. Notes will be posted, of course. Like the video that I'm creating, that will be posted as well. All right. Let's take a short break, and then we're almost done for today. But let's take about 5-minute break. Let's go drink some water and stuff, and then we'll continue and finish it up for today. All right, guys. So this is problem number 1, and we did it in great detail using both methods, and I also showed you residue function and everything. So you're going to be using all these things pretty much in many of the problems. So I will advise you again, go and then do it again, this problem, so that you can understand it better. Okay, let's see what this problem is then. This problem says that determine the solution of the following differential equation. Initial conditions are y0 is equal to 1, and differential dy over dt of 0 is equal to 0, and rt is equal to 1, t greater or equal to 0. So again, this is just the application of Laplace transform and how you're going to find the solution using Laplace transform. So let's do it quickly. So when you apply the Laplace transform on this, generally we write this down as Laplace transform and then Laplace transform. When we are applying Laplace transform, that's how we write down inside the braces. So when we apply the Laplace transform on this, what we are going to get? Laplace transform of the second order derivative. Let's go and check. Laplace transform of the second order derivative right here is going to be s square fs minus s to the power 2 minus 1, that is 1. So s f 0 negative, s k minus 2, that is 2 minus 2, derivative of f 0 negative, and so on and so forth. So for us, let's go back. So let's write this down first. The Laplace transform is going to be s square ys minus s y of 0 minus s to the power 0, which is 1, derivative of y evaluated at 0. And I'm going to ignore the rest of the terms because it's not going to be any term after this, plus 4 times dy over dt. dy over dt is going to be s times ys minus s to the power 0, y sub 0. S to the power 0 will be 1. So minus y sub 0 and plus 3y plus 3 ys is equal to 2 times rt, so 2 rs. So this is what I wrote down from my table, using my table. Again, let's go back to the table just to see. This is my table, and I'm using this function right here, this one. Laplace transform second order derivative, s square fs minus s to the power 1 f of 0, 0 negative, 0 is the same thing, minus s to the power 0 derivative, first derivative, evaluated at 0. So that's for the first one, and the second one will be d to the power first derivative of ft, s to the power 1 fs minus s to the power 0 f of 0. So that is what I used to write down the Laplace of the first term and the Laplace of the second term. And then, of course, 3 times y of s plus 2 times r of s. So let's go ahead and put down s square y of s minus y of 0 is given as 1. That's going to be s. And the first derivative of y evaluated at 0 is given as 0. So this is y is equal to 0. First derivative evaluated at 0. That's 0 plus 4 times sys minus 4 times y of 0. Y of 0 is 1, so minus 4 plus 3 times y of s is equal to rs is 1, and the derivative of 1 is derivative of a step function. Basically, 1 is a step function. Derivative of step function is 1 over s. Two over s. So now let's go ahead and rearrange this equation. Remember, we have to find y of s. The y of s is going to be on the one side of the equation. S square plus 4s plus 3. And then I'm going to take rest of the stuff on the other side, equals 2 over s minus s is going to go on the other side, it's going to become plus s. And then 4 is going to go on the other side, it's going to become plus 4. Okay. So now I have ys is equal to ys is equal to 2 over s plus 4 divided by s square plus 4s plus 3. The numerator is going to be 2 plus s square plus 4s divided by s times s square plus 4s plus 3. So this is my y of s, polynomial over polynomial. S, the denominator, of course, you can multiply by s, so s cubed plus 4s square plus 3s. And we have to find y of t. So we're gonna do partial fraction decomposition and then use the table to go back in the time domain. And to do partial fraction decomposition, now I'm going to use the residue function for this one. So let's go ahead and use the residue function. Numerator is 1, 4, 2, 1, 4, 2. And the denominator is, I'm going to multiply s and the other factor. So it's going to be s cubed plus 4s square plus 3s. So s cubed plus 4s square plus 3s. And since there is no constant, that is s to the power 0, we're going to put a 0 for that. So this is important that you understand it. If you have to go from the coefficient of the highest power of s to the lowest power of s. If any power of s is missing, that is the coefficient is 0, you will have to put that 0 for that coefficient. So in this case, since the coefficient of s to the power 0, that is the constant value, is 0, I'm going to put a 0 over there. If you don't do that, you're going to get incorrect result and everything is going to be incorrect. So make sure do not make that mistake. If a coefficient is missing, you have to put a 0 in the residue function for that coefficient. So these are my result. Let's go ahead and copy this real quick. All right, so what do I have? I have ys. This implies ys is equal to, these are the roots of the denominator. So I'm going to start with the root 0, s minus 0, that is s, which will be this root s, and the numerator for that is 666.67 exponent negative 3. So 0.667 over s. Then the second root is negative 1. So I'm going to do s plus 1. And the corresponding factor is 500 exponent negative 3, which is 0.5. And the third root is negative 3. So the factor is going to be s plus 3. And the corresponding value is negative 166.667. So I'm just going to use a negative sign over here and then put 0.1667. 0.167. So this is the partial fraction decomposition. And now, very simple, we're going to apply the inverse Laplace transform. What's going on? Or it is disappearing. Inverse Laplace transform. All right, who is going to tell me when I apply inverse Laplace transform, what will be my yt? Look in the table and tell me what will be my yt. Go back to the table. Okay. 0.667 what? Just 0.667? Huh? Ut, yeah. 0.667 ut plus, okay, 0.5 times e to the power negative t, yes. Negative 3t, very good. And e to the power negative t and e to the power negative 3t, we'll also put ut because our input is starting at t is equal to 0. So I'm going to write this down as 0.667 plus 0.5 e to the power negative t minus 0.167 e to the power negative 3t, and everything is going to be ut. Now, if you're trying to find the partial fraction decomposition without residue function, the process is going to be the same as we did in the last problem. Actually, it might be easier because you don't have any complex numbers in here. This is an overdamped system. So all the values in the numerator are, or all the roots, sorry, all the roots in the denominator are real roots. There is no complex root. But the process is going to be the same if you are trying to find a, b, and c. It's going to be a over s plus b over s plus 1 plus c over s plus 3. So you're going to multiply both sides by the denominator of a, evaluate at the root of a to find a, multiply both sides by the denominator of b, evaluate at the root of b, and then multiply both sides by the denominator of c, and then evaluate at the root of C in order to get 0.167 negative value. I did not show everything. I just used the residue function, but I will advise you to do it without residue, that is find the partial fraction, and then do it with residue as well, both of them, just to get more practice. But most of the time we're going to be using residue function. So very simple way to solve this, as you saw, using the tables. Delete this, we don't need this slide, so delete and delete. Okay, the last, I think this is the last thing that we have to do today. Let me look at the, as I said, I want to be as close to, yeah, final value theorem is the last topic that we are discussing today, so we are going to finish before time. Okay, what is the final value theorem? Basically, final value theorem tells you how to find the final value or a steady state value of a system. That is when time hits infinity, then how the system is going to be behaving. That's what final value theorem tells you. So generally in the time domain expression, if a time domain expression is written, you can look at the expression and you can tell pretty much right away the final value is going to be this. So for example, when we have this expression written and I ask you what will be the final value of the system, and your answer is going to be, what will be the answer? Huh? 0, yeah, exactly. Why? There is no. Just from the equation. Because of the exponential function, it's going to go down to 0, right? But as time increases, exponential function is going to start becoming smaller and smaller. Eventually, it's going to hit 0. So the final value of this is going to be 0. But what if you can find that final value not going to the time domain, but when you are in the Laplace domain, in the S domain, and you have the Vs written. Where is the Vs? Right here. You have the Vs written over here. What about if you can find the final value from that Vs without going into the time domain? That's what the final value theorem is all about, that you don't have to go to the time domain in order to find the final value theorem. So the final value theorem, it says that to find the steady state of the final response in the Laplace domain, we can apply this, that as time tends to infinity and you evaluate the value in the time domain, it's the same thing as in the Laplace domain. You multiply the Ys by S and then put the limit S is equal to 0. So again, let's take the example of, where is it? Let's take the example of this. So for this, what will be the final value in time domain? You can see that, right? It's going to be 0.667. 0.667, that's going to be the final value. Now, if we apply the final value theorem on this, so this is our equation right here, s squared plus 4s plus 2. So let's see. From the previous problem, limit t tends to infinity, Ys of t is equal to 0.667. So we know that, right? Now you apply the final value theorem. Limit s tends to 0, s times Ys, which is limit s tends to 0, s times expression of Ys was s squared plus 4s plus 2, s squared plus 4s plus 2 divided by s times s squared plus 4s plus 3. S times s squared plus 4s plus 3. So you apply the limit. The first thing we're going to do is we're going to cancel out this s and s. And then we apply the limit, put s is equal to 0. So when we put s is equal to 0, this will become 0, this will become 0, this is 0, this is 0, and you're going to be left with 2 over 3, which is 0.667. Right? This theorem is universal, so you will always find the same thing. Yeah. What is that? What do you mean just change s to 0? This theorem is always going to be valid. But basically, it is relating the time domain with the frequency domain, right? In the time domain final value, you find always when you let the time go to a very large value and then see how the system is behaving. If it is reached to the steady state, it's the the constant value, like in this case, it's just DC value 0.667. Or it is 0. If it is exponential function, it's gone down to 0. But if you are in the frequency domain, then you can apply that limit as tends to 0 sys, and you're gonna get the same final value. So instead of doing all the derivation or plotting the function or whatever, and then looking at the final value in time domain, you don't have to do anything if you just know how the system is going to behave when it will hit the steady state. What's the significance? They're canceling out. I mean, if they're canceling out, you cancel them. What do you mean? You don't want to take the variables if they cancel out. You don't take those variables in the next step. Otherwise, it's just going to become more complicated. You're right. So whenever something is canceling out, just cancel it right away. If there is an s, what do you mean in the denominator? No, this s is coming from here. It's not. There's no factored out s. This s is this. This is your y of s. This is your y of s. So this y of s can be anything. In this case, my y of s had an s over here because we excited it with a ut function, a step function. That step function had an s over here. If we did not excited it with the ut function, let's say there is no s over here, then what will be your final value? 0, right? Because this is going to be 0, and when multiply 0 to 2 over 3, the final result is going to be 0, right? So if you are not exciting this function with a unit step function or a step function, then the final value is going to be 0. A steady state value is going to be 0. It's going to go down to 0. In this case, you have a DC value as your final value.